Hello there, hackers. How are you today? It's great to see all of you back for this workshop. And send a message in the chat if you are returning from a previous set portion of this workshop. I see some familiar faces, but also some new faces in the chat. Yeah, I mean, regardless, it's great to see you. Hi there, Asmam and Bugbreaker, some familiar faces from our last series sections, our last parts of the workshop. It's great to have you here, and I hope that we can cover some things that you all are interested in. We're actually going to take a quick moment at the beginning of the workshop today to talk about some data science concepts that were requested at yesterday's Today in Global Hack Week section. Someone requested that we talk about Conda environments and building development environments through that tool. So we're gonna take some time today to actually go over that process. But yeah, did anybody see any streams yesterday? And if so, what was one that stood out in your mind? Did you learn anything new in yesterday's workshops? I'll tell you, yesterday I participated in the Today in Global Hack Week stream, and I was able to see some of the posts that you all made of your workstations and your swag that you got. And yeah, it's great to just see so much excitement and positive vibes in our community. Okay, we see some Linux strip workshop. The random forest, I think, is what that is referring to. So that's really great. Thank you for sharing. Yeah, Linux scripts can be tough. But anyway, Shinigami says, can you share the registration and check-in link? Thank you for that transition. That's really great. So actually, yeah, I am going to share that. Let me send it over. Okay, so you should see a link in the chat. You can also find this link in Discord. It's the link for us to check in today. No, it's all good. Thank you for reminding me, Shinigami. So yeah, this is great. We're going to check in because that's actually going to help Major League Hacking know what kinds of things you all are interested in seeing. And we have a really excited workshop planned today, and that's because we get feedback from all of you on what you'd like to see and what you're interested in, and checking in is one way that you can do that. So really appreciate it if you can check in using this link in the chat. Everybody, yeah, and it's funny actually. I noticed that this screensaver that I'm using has a clock in it, but the clock is always set to the same time, so it's a little disorienting actually. um, but yeah, so anyway, that's the check-in link, and we're going to be doing a review of what we did last time. But before we do that, I want to actually clue you all into Conda. So we had a request to talk about Conda before, but let me just show you their website first, and then we'll dive into an actual installation. So this is the Conda website, and you can learn more about Conda. It's basically a way for packaging or installing packages in your environment and keeping those packages separate from each other. Because when you install many, many different packages, it can cause a conflict. And so That would be really bad if you're trying to have consistency in your developer environment. So let's actually go. I'm going to share anaconda.org, which is the particular software that I use, and you can download that at www.anaconda.org. So I highly recommend that you download this product if you are interested in Python, and yeah, using Python for data science and or machine learning, because it's going to be really useful. And I'll show you exactly how it is useful in a minute. All right, we're actually going to look at a few installations here. So I'm gonna show you one. Okay, this is a super useful tool. It's called Stats Models, and Stats Models stands for statistical models. And so you can actually download this package using the conda command by saying install conda install. Then there's this -c keyword, and -c, that flag stands for channel. So we can choose which channel we want to install from, and the Anaconda channel is the default channel, the most common one. And then we have Stats Models package, and this is really similar. You may have heard of this before, pip. So if you've heard of pip before, there's also a way to install Stats Models with pip. And you might ask, why would I want to install with Conda if I can install with pip? Well, Conda is going to make sure that when you install this new package, it doesn't break your environment. It doesn't cause any issue with two packages, their needs and their dependencies colliding with each other. It's going to avoid all of that. So it's very recommended that you use the Conda installer over the pip installer for certain applications. And had a request in the chat to share social link, so I will go ahead and share my LinkedIn. I have no problem sharing LinkedIn, and I love it when hackers connect over LinkedIn. So please feel free to send me your requests if you're interested. But anyway, now I'll move on to another package that I want to talk about. This is one that I think is really cool. And, a lot of people actually use this one for GIS, geospatial applications. And it's called Region Mask. It's for masking out a region that you want to make a plot of. Let's say you want to make a map of California, for example. You don't want to put the ocean in that map or any other states or countries. You just want California. And so you could use Region Mask to do that. But there are two ways of doing it. Again, you can use pip install Region Mask, or you can use Conda. And Conda will use the Conda Forge command channel. So there's multiple different channels, and yeah, that can be really great tool. But yeah, let's actually go into a Conda terminal, and I'm going to show you just how this works. So let me present. My terminal. This is my terminal on my personal computer here. And I'll show you that you can have this command called conda env list. right? And I have these two Conda environments. Right now I'm in my base environment. To activate a different environment, you can activate it this way. So I just type Conda activate, and I'll just type the name of the other one. And to switch back, I can type Conda activate base, or I could type Conda deactivate, which would also revert back to the base. Now, if I want to see what packages are installed, I can type, I believe, Conda list. Yeah, and you can see all of these packages are defined for the base environment. And a different group of packages will be defined for the Pangeo environment. And any other environment that I'd like to create, I can create using conda commands. And then if I want to run a Python file, like let's say I just had some test file, it could take advantage of all of these packages that are installed in the environment. And so that's really great for keeping your environments consistent time after time. There's another command, I think it's conda create. Yeah. So you can do conda create, and you can actually use -f, and this stands for file. You can see over here. And you could use a requirements.txt file, or you could use a environment.yml file, any kind of metadata file, which can store the information about a particular environment. And then you can upload that to GitHub or whatever version control system you use. That way, other developers can create a specific environment with all of the packages that you want to use for your project, and they don't have to worry about installing all of those on their own. And yeah, Bugbreaker says, is it better to create unique environments of each project? Mom, it definitely has the right answer there. And it's because your project's dependencies, you don't want those to interfere with another project. So if you want to be really, have really good practices, you would ideally create a new conda environment for every project that you do. Okay, so hopefully that answers some folks' questions. These are basically virtual environments. You're creating a different one. You can just kind of spin one up in your terminal here. Yeah, that's the other danger is you can end up with a lot of environments in your system and not know exactly what to do with them. So that's why I recommend creating a requirements.txt or environments.yml file. That way, and attaching that somehow to your repository or your project. So that way you can actually get that whenever you need it. And it helps your project be reproducible as well. All right, any more questions about Conda? Yeah, so the question about Docker. So Docker is, it's a slightly different tool, and Docker can actually be useful in other ways because, when you create a requirements file using Conda, it's actually specific to the operating system that you're running on. And so Docker is actually going to tell you even more information about exactly what kind of environment this code was executed in. But Docker can be a little more complex, and it can be used, you can use that in conjunction with Conda depending on your specific needs. So I would highly recommend learning about Docker as well if you're interested in this sort of thing. And yeah, I don't know if we have any Docker workshops during Data Week. But yeah, we definitely have Docker um, workshops that have been pre-recorded. So if you're interested in learning more about that. It says, can we use pip to install Conda? I don't think so. I don't think you can use pip to install Conda, but I could be wrong about that. So if anybody in the chat knows, um, let us know. As far as will there be a swag drop today? Not on this stream, but yeah, I think usually during the Today in Global Hack Week stream, that's the best place to ask questions like this, and it will happen really soon, in just an hour and a half or so. They will have that stream. All right. Well, that's enough of Conda since we've sort of covered all that we can about Conda. But I'm actually going to return to our Markov decision process slides today, and we're actually going to review those one more time because I think that yesterday we went kind of fast through them. And so today we're going to try and maybe review them and see if anybody can maybe get a little bit out of that. So we talked about this yesterday, but Markov decision process is a reinforcement learning algorithm. And this is a less common type of learning than supervised and unsupervised. I think most of the time people learn about supervised first, and then maybe they learn about unsupervised, but rarely do they get to reinforcement, which is what we could also refer to as a semi-supervised learning algorithm. And the reason it's semi-supervised is because we are asking the algorithm to design a policy, an ideal way of making decisions, but we are going to prescribe a scenario to the model. And the scenario has a lot of constraints that are human imposed, like what states can you be in? What transitions can you make between states? What actions can you take? And what outcomes could occur? So here was our example from last time, which we had two states, which was San Francisco, and then Los Angeles was our final state. But actually, you could choose three different pathways. So you could choose to go to the train, the car, or the plane. And we found that the ideal way to travel, if you want to take the least amount of time, is to travel by plane. But then we made our travel scenario more complicated, and we found that you could add in certain probabilistic transitions, which also incur outcomes. So when you have this transition to severe traffic, it gives an outcome of 1 additional hour in the car. And we changed our plane, made it more complicated and more realistic by adding in some chance of security delay, plane delay, deplane delay, and things like that. And then we said, let's imagine that our optimization is not as simple as let's get to Los Angeles as fast as we can. Let's imagine that we have a really important meeting in 8 hours. And maybe you got a notice in the mail that you have jury duty in Los Angeles, and the court date is set for a certain day and time, but you've been in San Francisco, so you need to get back absolutely at that time. But you also don't want to spend more time than you need to in travel. So if that's the case, then we found that after we did some investigation of the different possibilities, we actually found that the best way to travel is to travel from San Francisco to the airport and then wait in line in security. And if you get through security after 1 hour, then okay, go on the plane. But if you don't get through after 1 hour, that means that you hit a security delay. And so you should immediately return home get in your car and drive to Los Angeles. So this kind of a decision actually is something that we might need a computer to help us find. It's not as intuitive as you might think. And actually, once we go to more realistic scenarios, we can get into even less intuitive examples than this travel one, which is one that you probably experience regularly. This idea of how do I travel from one place to the other in my using my time as best as I can. Yeah, Bugbreaker 18 says, what do we call these probabilistic events? Yeah, you can call them probabilistic events. You can also call them states, which we will get into in the next slide. And so another way you can call them, which is the way that we formalize this, is we call it a Markov process. Okay. And so if you go on Wikipedia and you look up a Markov process or a Markov chain, I think I have this here. It's a stochastic model. That means that it's a random model. Hence why we have 10% traffic chance or 25% chance of a delay. Describing a sequence of possible events in which the probability of each event depends only on the state in the previous event. So here is an example given to us by Wikipedia of a Markov process. And so imagine that you are in state number A, or state letter A, not number. There is a 60% chance that you will stay in state A, but there's also a 40% chance that you will move into state E. And also, in this diagram, you can see that if you're currently in state E, then there's a 30% chance that you will remain in state E, but there's also a 70% chance that you will transition into state A. And so this is really forming the backbone of what we call Markov process. And you'll see from our slides that this example really resembles a Markov process almost perfectly. So here we've prescribed different states to these events and situations that we describe. And so you can assign probabilities to each of these state transitions. So let's say that we have the transition from 0 to 3. There is a 10% chance of that transition happening if you choose to take the plane route. And then if let's imagine you choose state 1. If you're in state 1, there's a 10% chance that you will incur traffic and transition into state 2. But if you do not hit severe traffic, there's actually a 90% chance that you will transition to state number 7, which is go all the way to Los Angeles without any traffic. And meanwhile, there are outcomes like the train, which is in state number 6, where there's actually a 0% chance that you will transition into the plane, for example. I mean, there's no way to transition into the plane from the train. You would need to go back to San Francisco and get to the airport. So we could assign that probability transition with 0 value. Right. So this is kind of just showing you that there's an analogy between the Markov process and the kinds of decisions we would need to make in a travel scenario like this. Okay, so now we're going to talk about the state transition matrix, which we talked about earlier. This is a super interesting question from Asmam about the finite state machine concept and probability. And actually, I'm not really sure. It's been a long time since I thought about finite state machine. Um, oh, I guess this is yeah. I would guess that there are some analogies you can make between the finite state machine model and the one that we're looking at with Markov process. But I'm pretty sure that they're not exactly the same thing. So you might need to. But that's a super interesting question. Yeah, keep in mind that the Markov process is a stochastic model, so it's random, and not all of those finite state machine models are random. So that would definitely be something to keep in mind. But yeah, that's a super interesting question. So yeah, let's return to our state transition matrix. And we talked about this yesterday, but P12 is the probability that state 1 will transition into state 2. And so this is in our case, this is the probability that if you are currently in state 1, this is the probability that you will in the next iteration, you will be in state 2. So imagine we're currently in the car. Okay, that has to be true. And if we are currently in the car, then there is a 10% chance that we will experience severe traffic, which is the state 2. So that probability is 0.1, and we would fill that out in the probability matrix here. We also had the rewards matrix, which we talked about last time as well. And this is calculating the reward for each action. And you could either maximize the reward or minimize the reward. So in our example today, we're actually going to be maximizing the reward. But in the example from yesterday, where we did our San Francisco to Los Angeles trip, we actually wanted to minimize our reward because we don't want to take a lot of time to travel between these two cities. Okay, and so this is the example we'll be studying today, the forest management. And I have this example from a previous workshop, which was for Social Good Week. And Social Good Week, I highly recommend if we ever do a Social Good Week again. Stay tuned. But it was great to learn about because we actually saw an application of the Markov decision process to forest management. And so with the forest management, we have actually forest age as a great state diagram. So it only depends on the state that you're currently in. I mean, if you're in the new forest state, whether or not that becomes a middle-aged forest is entirely dependent on probability in this model. And then in a mature forest, you can only transition to a mature forest if you're already in the middle-aged forest state, right? You can't just skip over this middle age and go all the way to maturity. Just like people can't skip from high school into retirement, most people. Um, but so this is the idea here with the state diagram. Anyway, so then we can assign some probabilities to the transitions. So this probability, which is P01, if you remember from our matrix notation, is 0.9. It's the probability that the new forest will transition into a middle-aged forest after let's say after 1 year. So there's a 90% chance of that. But there's also a 10% chance that there will be a fire. And if there's a fire, then a middle-aged forest could turn into a new forest. Okay. So this could happen if you're in the middle-aged forest stage. There's also a chance that this will happen in the mature forest as well. So we could have a 90% chance that the middle-aged forest will grow into a mature forest. But then once it's mature, every year there is a 10% chance of fire. And when there's a fire, the growth goes back to the S0 state. All right. We also had the rewards matrix, right? Every time we do a Markov decision process, we have to define a rewards matrix as well. And keep in mind, these are things that we are basically human assigning, right? I assigned this. Maybe I looked at some data and I realized that fires happen once every 10 years, or some other thing. But that's why we call this semi-supervised learning, because actually humans are actually giving some information into this process. So here's the rewards matrix, and we can say that we cut the tree. This is one choice that we have. If we cut the tree when it's a new forest, then we will get $0. If we cut the tree when it is a middle-aged forest, then we will get $1. And if we cut the tree when it's a mature forest, we will get $2. So that's the idea with this cut decision, is that the more wood we have, the more money we'll make. On the other hand, we can decide to keep the forest. And if we keep the forest and we don't cut it, we will not get any money because we won't be getting any wood. But let's imagine that if we get to the mature forest stage and we keep the forest intact, the government will pay us $4 because they want to preserve the forest to fight climate change, maybe, or maybe they want it for people to be able to go to and for recreation, or they want it for the ecosystem. Whatever the reason is, the government will pay us this reward to keep the forest in its mature state. And actually, you'll notice that mature state for $4, that's actually more than we would get for cutting it. Right? So what would you do in this situation? What would you do to maintain the forest? But we will be talking about that today. And we're actually going to use the MDP toolbox to get started with that. And MDP toolbox is a Python library that implements the Markov decision process algorithm. And so I want you to visit this site. I'll actually send you the link to this site. And maybe I'll even send you the link to these slides, because we're actually going to be using these slides next. Or you're welcome to use these slides as a reference. Yeah, so this is the link to the MDP toolbox. And if you all can go to that documentation, it'll show you how to install MDP toolbox. We'll go over it ourselves anyway. The second link that I sent was a link to Google Docs, where you can see the presentation that we just looked at. In case you had any questions or you wanted to review any material. And the third link I'll send is to the Python notebook for today. And this is a link to my GitHub repository on ML classification. And the reason why I still have this as a classification algorithm is because we are going to be saying choosing between discrete options. So one option is cut the forest. The other option is keep the forest. And so for that reason, it is still we are classifying scenarios into decisions. All right, so now let's move on, and we're going to actually discuss lesson number 3. That's right, as Bugbreaker says, decisions are classified. And so, that's sort of why, in my view, it fits under this category. But yeah, we have a lot of material that we've covered already in lessons 1 and 2. And we did that through our Visual Studio Code Editor, or whatever code editor you have at home. So you can just put lesson 3 notebook in there. And that will be a great way for you to get started. But yeah, let me share my screen and show you all. So I have my editor pulled up. Hopefully you all can see that. All right, and we're going to start by importing the MDP Toolbox library. All right, so you're going to do this command, pip install PyMDP Toolbox. And it will run and install PyMDP Toolbox. You might be asking, hey, why aren't we using Conda for this? I'm actually not sure if there is a Conda implementation. Sometimes a library does not have any Conda implementation, but that's okay. We can still use pip. And so now that we've done this installation, it doesn't take more than a few seconds on most computers. We can go into importing the relevant libraries. So we'll import first from MDP Toolbox a module called example. And this is going to be where we get some information about our forest management. We'll also import from MDP Toolbox MDP, which is how we get the solver algorithms for our scenario. These algorithms will optimize and find a policy for us. Finally, import NumPy as NP because, well, we always are using NumPy, right? Okay, and I'm going to copy and paste from my solution notebook some information about this forest management. It's stuff that we covered in the slides, but I just want to have it here so that you can see it as well. All right. So here's the text from the notebook. You can see this text if you open up the notebook on GitHub. But basically, it's just reiterating what we talked about in the presentation. So trees can either be young, middle-aged, or old, and that will give them a state, which is either 0, 1, or 2. And each year, these trees get one stage older, so their S goes up by 1, unless they're middle-aged, or I'm sorry, unless they're mature, and then they won't get older. Each year, there's a 10% chance that the whole forest burns down. And if it burns down, you get nothing. If you cut down the trees, you get nothing unless they are middle-aged or old. Then you can get some amount of money from the wood. But if the forest reaches its oldest state and you choose to keep the forest around, you'll get 4 points or $4, let's just say. So what is the best strategy given these facts? We're going to look into it. And so our inputs, talk about it. We have S, which I say capital S, is the number of states, the different possible ages. R1 is the reward you get when you wait. So this is the reward that you get from waiting given a state S. Okay. So let's say that you're in the young forest state, what's the reward that you get when you wait? Well, it would be 0. You won't get any reward. So R1 would be equal to 0 in that case. And R2 is the reward that you get when you cut, given the state. And P is the probability of a wildfire occurrence. So this is really saying the probability of a transition, right? Because the only two possibilities are wildfire or growth. These are our inputs into the model. And the outputs from our example, this is from our example module. All of this is for our example module. Construct the scenario, right? That's what we're doing right now. It's going to give us some outputs. One output is P, and P is going to be an object that is the transition probability matrix. That's what it'll represent. And it's going to be a NumPy array of shape A, S, S. So that means that A is an action, S is a state. So let's say that you choose cut, that would be A equals 1, and so forth. And then R would be the reward matrix of shape S, A. So that means that we'll have a state and an action, and it will return the reward. All right. So now let's actually do this. We'll type P, R, which will give us the two different objects. And we'll type ndp toolbox .example.forest. Okay, so this is for our forest example. And we're going to keep it really consistent with the slide. So we're going to say that S equals 3. So we only have 3 ages for the trees. And we will say that that R1, which is the reward for when you wait, is going to be 4. And R2 is equal to 2. And T is equal to 0.1, which is the probability transition. And we also use this is sparse to tell if the matrix is sparse, and we'll just write false there. So now we can run this cell, and let's see what P looks like. All right, so this is our P matrix, and you can see that the first 3 by 3, this is associated with action 0, which is to say the action of waiting. So if you wait, and let's say you're in state 0, so that is the new forest. If you're in state 0, new forest, and you wait, then you have a 10% chance of staying as a new forest. And why? Well, that's because the forest could burn down before you even get started. But then there's a 90% chance that you're going to transition into a middle-aged forest. If you're a middle-aged forest, then you have a 90% chance to become a mature forest, but also a 10% chance to become new, and there's 0 chance that you will stay that way. Same with a mature forest. On the other hand, if you choose to cut down the forest, it will always return to new forest, no matter what state you're in. So there's a 100% probability assigned to new forest for those transition matrix outcomes. Okay, so there you go. And hi there, John Paul. Welcome to the stream. Okay. That's right. This is the state transition matrix if you wait, and reward matrix. We'll talk about the rewards matrix later, but this is for both essentially. So this is the state transition matrix if you wait is the first one, and the state transition matrix if you cut is this one. So this is just telling you what the state will do. But now we'll look at the rewards matrix. Okay. So with the rewards matrix, you can see the first column here. This first column is describing what the reward will be if we wait. So imagine that we choose to wait and the forest is in state 0, which is the new forest state. If we choose that option, then we get $0. If the forest is in the middle-aged state, we get $0 too. But if we make it all the way to the last state, then we get $4 from that forest. On the other hand, if we have our rewards matrix here where we cut, then we get $1 for middle-aged and $2 for mature and $0 for new. All right, so now I have a few problems for us to do. So let's do them. So the first one is, what reward do we get if we choose to wait and the forest is in its oldest state? Well, we can check that by looking at the rewards matrix. So if we choose to wait, that means we'll be in this first column. So we'll do RT0. That's going to give us the first column. And if we are in the oldest state, then that means that our state vector is 0, 0, 1. Right? And so our reward is the total of this. Our reward is $4. If we choose to cut, all we need to do, let's say we choose to cut, all we need to do is change to the first column. Now we see our reward is $2. Okay, so this is a really good way of using math to describe a situation. All right, now we're going to find the optimal policy. And this is where the actual Python coding algorithm comes in. Right up until this point, we've just been doing, matrix algebra, which is pretty hard, actually. I don't mean to say just been doing matrix algebra, but I mean that we have more to the puzzle, which is the actual optimization. Okay. And so before we get into that, I just want to address a comment. So if you're new to ML and AI, I highly recommend you check out our previous streams, which are all recorded, available on YouTube. And we actually even had a machine learning week a few months back. I think it was in March. And you're welcome to check that out. So yeah, don't worry if this is a little bit too much to digest at once. You can always check out our other resources. They're super, super useful, and you can go at whatever pace you want. That goes for anyone in the chat, actually. But yeah, thank you for that comment. All right, so now let's go on to finding the optimal policy. And so in this case, we're going to use the MDP package. So we'll type model, because remember, we're going to define a model, and we'll use the MDP toolbox.mdp module, and we're going to use the Q-learning method. And the Q-learning method is just one algorithm for Markov decision process. And it's essentially a reinforcement learning algorithm that is going to learn the optimal policy. It's going to maximize the reward, and it's going to do that over multiple steps and just sort of figure out through its algorithm the optimal policy. Okay. So there's a few inputs that I need to give to the Q-learning model. The first one is the probability transition matrix. It needs that, and it needs the rewards matrix second. These are going to define the scenario for the Q-learning model. Otherwise, it doesn't know what it's optimizing for. And there's one more element that we need, which is the discount rate. And the discount rate I'll talk about in a minute, but let's just use 0.1 for now. All right. So now we're going to type model.run. That's going to run the model. And we'll type model.policy. That will output the policy. Okay. Oops. Not Markdown. That'd be cool if you could run machine learning algorithms in Markdown, but we get our result, which is 0, 1, 0. And you might be thinking, what does this mean? What does this model policy mean? Well, here's an application. So let's look at this first prompt. Should we weight 0 or cut 1 in the youngest state? Let's check our policy. If we type model.policy, let's look at the youngest state, which would be the 0 state. And let's see what the policy value is in that state. So the policy value is 0, which indicates that if the forest is in the youngest state, we should wait. And that's pretty intuitive, right? I think most of you would have guessed that because actually there's no reward to waiting or cutting in the youngest state. But if we wait, we might get a bigger forest that we can start getting rewards from. Okay. Now let's check the second one, which is should we wait or cut in the second youngest state? So we type 1 in our policy, and we find that if you are in the second youngest state, you should definitely cut the forest because you're not sure if it will grow into a mature forest. And then if you're in the mature forest stage, so let's say you already have a mature forest, you definitely should not cut that because you will earn a better reward, right? Okay. So now we are going to talk about discount. And discount is a concept that we have in Markov decision process. But before we do that, I want to answer some questions in the chat. The first one is, can we customize the amount of rewards? And the answer is you absolutely can. So just change the values of these matrices. So you can input whatever matrix values you want here. The only reason I chose to use the forest example to build these matrices is because it can take a long time to build them. So I just used this module to easily build one. And then Osmom says, same thing happened to me yesterday. I spent 10 minutes wondering why my code was not running and then realized it was a markdown cell. Yep, it happens to everyone. Thank you for sharing. Yeah. Oh, you can create your own PNR matrix if you want. Yeah. So if you want to create PNR, here's a challenge for you. Maybe try to create it for our Los Angeles, San Francisco example. It can be pretty challenging though. Yeah, because you have to consider every transition, but it's definitely possible to do, and actually possible to do under any scenario that you have, as long as that scenario is a Markov process. Yeah, exactly. It's a lot of states. So we're only dealing with 3 states here, and you can already see how big the matrix is, right? In the Los Angeles, San Francisco example, we had 7 states. So it's going to be a 7 by 7 matrix, and there's actually multiple choices you can make. You can go to the train, go to the car, go to the plane, and so on. You can return back to San Francisco. So there are multiple decisions. There are many more decisions as well. So you can see these matrices get pretty large, and the math gets more complicated. But yeah, now I'm glad we were able to answer some of these questions, and we're going to move on to the discount, which is applying a discount to our model. This is a discount. We'll talk about it. So before we set discount to 0.1, and discount is actually the likelihood that a scenario will continue in the future. Okay, so what that means is that sometimes we're not sure if the same strategy is going to continue to work over time. Like for example, let's say that this scenario we've envisioned might change because of the fact that the government might increase the reward, right? And if the government increases the reward and you already have a mature forest, lucky you. You're going to have a huge windfall. Um, let's imagine another scenario where you lose your forest somehow. Maybe you need to give it over to someone else for management. Maybe the government takes it or something. If that's the case, then you can no longer make any money from the forest. And so that would mean if you think these things are likely to happen, you want to set the discount really low. But anyway, let's play with a high discount rate now. So we're going to do the exact same Q-learning algorithm, but we're going to set the discount rate really high to 0.999. A 99% discount means we really think the scenario will persist. So we think that this deal where you get $4 for waiting and $2 for cutting, we think that's just going to hang around for a really, really long time. Well, if you think that's the case, let's run and see how our policy changes. All right, you can see our policy's changed. And so now the algorithm suggests that we wait no matter what state the forest is in. So the forest could be in the middle-aged state. And even though we could get $1 for cutting, and in fact, our low discount policy suggests we do cut that tree down, if our new high discount policy suggests that we should not do that. It says, hey, wait until you get the best reward possible. Okay. And some of you asked about transition matrices and solving large transition matrices. But let's actually look at an example here, which is random example. So this is giving a random transition matrix here and a random rewards matrix. So you can play with these random ones if you want to get more practice handling these probability transition matrices and these rewards matrices. All right. So that's it for our Markov decision process. And I hope that you all were able to learn about this. Yes, exactly. States and actions. So S would be the number of states. You can just say as many as you want. And actions would be number of A. So this would be 4 and 5, for example. All right. Well, we are going to take a 10-minute break, and then we'll come back, and we're actually going to start a new module called transfer learning. And so we are not going to finish transfer learning today, but we are going to start that. And it will be another way that we can use machine learning for making decisions with data. And actually, in this case, we're going to be using image data. And I know there were some folks excited about image data at the beginning of our session. And so we'll get to take a look at that when we come back from the break. Before we go on break, though, I just want to make sure that no one has any additional questions about Markov decision process. So I'll wait for just a minute. All right, awesome. I'm glad you're working on images, Firegraver, because we are going to actually do some detection today from our images. Maybe some of these concepts will be useful. All right. Well, it doesn't seem like anyone has any questions about Markov decision process, so that's great to hear. And I will see you all back in just 10 minutes. Make sure to get up and stretch, grab some water, grab a snack. All that stuff is super important. All right. See you soon. All right, everybody, we are back from our break, and welcome back to the stream. It's great to have you all here, and yeah, we're going to be beginning today's second half by talking a little bit about plants. You might be thinking, what do plants have to do with technology? Well, a lot actually. So let me start off by sharing with you all a folder. And we're all going to look at this together on the stream, but I just wanted to share it with you so that you could look on it on your own if you so choose. All right, so this is in my Google Drive. And it's a data set that we actually get from Kaggle. I'll send you all a link to the original Kaggle data source. But the data is divided into 4 categories with 3 different plant diseases along with a healthy control. So here's a bunch of pictures of nice healthy leaves. Nothing wrong with these leaves. And then if we look at the leaf mold, we can see that some of these leaves have some yellow hints to them. There's another disease called tomato mosaic virus. And so these are some leaves which are known to have tomato mosaic virus. And a third disease, which we'll talk about today, which is two-spotted spider mite. So all these plants are infected with two-spotted spider mite. And, let me pose a question to you all, which is, suppose I wanted to figure out whether these plants had a disease based on whether or not their leaves, based on just pictures of their leaves and whether or not those showed any signs of imperfection. And I gave you this data set, and I said, why don't you construct an algorithm in order to tell me whether they have a disease? First, I'd like to ask you, is this a classification or a regression task? And remember, classification and regression are 2 different types of algorithms. I'll ask you all and see if okay, so we have many different votes for classification. Exactly right. And this is also exists on the spectrum of supervised, semi-supervised, or unsupervised learning. You could choose any of these, but there is one that will clearly be better. That's right. So it's supervised. And it's possible that you could use a semi-supervised algorithm, Bugbreaker, but if you think about the Venn diagram, I'll show that Venn diagram actually. Just give me 1 second to pull it up, because I think it's a really helpful one. for understanding the difference between supervised and semi-supervised. All right, here it is. So you might remember we called supervised activities, we called those recognition or discrimination tasks. So here we're asking recognize images is a supervised, firmly on the supervised spectrum. Unsupervised would be generation tasks, so we're imagining new things. And semi-supervised could be something in between. So with our decision making process, we're asking the algorithm to kind of imagine a little bit what might be the good strategy, but we're also saying, giving it lots of constraints. So we have a little bit of both. But in this case, I would call this a recognize images task, which falls strictly on our supervised learning spectrum. Okay, so we're going to be using supervised classification algorithm. And I had another comment that someone says, from the benches, these are Euro-worth problems, not just theory. I'm working with something like this. So definitely, thank you for that comment, because yeah, these machine learning algorithms can really be useful for things, for real world applications that have economic implications, like protecting your crops from diseases, for example. Okay, so we're going to be using a technique today that is called transfer learning. And I'm going to send a link here I always like to use Wikipedia. I just think it's a great resource for making simple, for learning about something really fast. But yeah, you can tell that machine transfer learning is a technique in which knowledge learned from a task is reused in order to boost performance on a related task. So think about this. A lot of machine learning algorithms are inspired by human experience. And so think about this, right? Have you ever tried to play tennis or badminton? Okay. You will notice that if someone is a good tennis player, they will also probably be good at badminton. And think about another example. If someone is already good at mathematics, it's highly likely that they'll be good at physics too, because there's a large overlap between those tasks. And so what's happening is that person is learning faster and improving their skills better because they already have some background knowledge. And transfer learning is this idea that we can apply this to computers too. So for example, for image classification, knowledge gained while learning to recognize cars could be applied when learning to recognize trucks. And you might be able to recognize where we're going with this, and recognize some of the benefits of transfer learning. One of the benefits is that transfer learning allows anyone to take advantage of really difficult to train models. So let me actually show you TensorFlow Hub, which is this website I'll send in the chat. We're going to look at TensorFlow Hub. It's a great repository of previously trained, or also called pre-trained, machine learning models. And you can see we're really interested in object detection for this application, but you can see there's many different applications. Well, here's just one example of a pre-trained model. It's been downloaded 8,000 times, and it's using the RCNN algorithm with ResNet v2. This could be really difficult to train on your own. You might need a supercomputer to train something like this. in an efficient amount of time. And it's trained on this large COCO 2017 data set, which is a large object detection data set. I'll show you that. Sponsored by all of these companies in AI. And yeah, there's just this example of all of these objects. Detect a bike, detect a plane, detect a person on a horse. And so by learning how to do this along a large quantity of objects, when it gets to your time, it's going to be much easier. And yeah, this data set is huge. You can tell that the data set has over 300,000 images, and over 200,000 of those have actually been labeled by a human. So someone went in and actually drew a line around the object. Pretty cool, right? And they have captions. So each image has 5 different captions. So it's just an enormous amount of data. And the idea with this pre-trained model is that maybe this model could be useful for your application and could be calibrated. 144 gigabytes. I didn't see that actually, but that's huge. I don't know exactly, but I would be really confident that it would be trained on a supercomputer, or definitely not a standard laptop computer. Yeah, most of these algorithms that have CNN, they are run on actually GPUs, because GPUs turn out to be more efficient for solving this type of algorithm than a CPU. And most laptop computers do not have a GPU, or if they are a dedicated GPU, and if they do, it's not a very large system. Oh yeah, I know the struggle with labeling. It can be tough. But anyway, this is our transfer learning concept. And so yeah, the idea is that, now that you have this model, instead of downloading 144 gigabytes of data and then training it on a supercomputer or just a high performance computer, and then calibrating the model, you can download this faster RCNN for just 200 megabytes, and then boom, you have it on your computer within a few minutes, and you can just go right from there. But all right, so we're actually going to be talking about the following project, which is on, it's actually on the TensorFlow webpage. And this is a notebook called Classify Flowers with Transfer Learning. And so this notebook is about deep neural networks, and it's about transfer learning, and we're gonna apply the concepts in this notebook to our plant disease detection algorithm. So the setup is that we import all of these items, and I'm actually going to share this notebook with all of you so that you have it. You can follow along. Okay. And then in the next session, we will actually adapt this notebook to our own purposes. So let's run this. You can run these Colab notebooks, by the way, in your browser. You don't even need to install anything. And that's one of the reasons why I recommended you try it for yourself. You can see actually Google has generously given us 12 gigabytes of RAM. That's a lot of RAM actually. And 107 gigabytes of storage just for free. Really an incredible service. So anyway, this flowers data set is is coming from this flower photos directory. We'll have our plant photos. The train fraction is the fraction of data we want to use for training. And you'll remember we did an 80-20 split for our kyphosis example in the last workshop as well. And random seed, this is ensuring that we get the same exact accuracy every time we run the notebook. So you remember from our kyphosis example, we had a different accuracy every time we ran the notebook. But in this example, we're going to have the same result because we're defining the random seed. It's not actually any better or, there's nothing really better about doing this. It's just one preference. So this is going to download the images, make the train and test sets. And so we'll do that actually. Just run that code. And once it runs, it doesn't take very long. We actually realize that there are 3,000 training images. So this is a much smaller data set than the 300,000 data points in a data set used to train a pre-train a model. But it's still going to be useful for us to fine-tune those parameters and really get a better outlook for this flower, get a better eye for these flowers. As 5 label classes, so there's daisy, dandelion, roses, sunflowers, and tulips. So what that means is that given a picture, our goal is going to be to figure out, discriminate against these different flowers, which makes it a supervised learning such a good choice for this. And there are also 736 test images. So these will be how we will evaluate the performance of the model, just like we did with our kyphosis example. Okay, so let's actually explore this a little bit. We're going to choose number image is 15 here, and we'll show some labeled images. You can see this notebook is just plotting these images. And the title of each plot is just the folder from which it came. So we have a rose, a dandelion, a daisy, and you know, based on your knowledge as a human, and maybe you know about these different flowers or some of them you're familiar with. A lot of people are familiar at least with roses and sunflowers, but you can figure this out yourself. But imagine you had like hundreds of thousands of these images and you really don't want to have to sit there and look at each one and see, is this a daisy? Is this a tulip? That's where our algorithm's going to come in. And yeah, this one is super interesting because I'm actually not sure how you could tell that's a tulip field, but I guess it is. So these data can just come in all different forms. And that's what makes it such a challenging problem. So now we have the build a model stage. And this stage requires us to specify a learning rate. So this learning rate parameter, which is 0.01 for right now. And it's going to actually tell us how quickly the model is allowed to converge. So what I mean by that is that the parameters of the model are allowed to adjust over time, but eventually they will settle on a solution. And this learning rate can slow that process down and say, hey, I don't want you to settle so far after just seeing a few images. I want you to actually, take a longer time and take more iterations to really settle on your solution. And so this learning rate, by setting this lower, we can typically increase the performance of the model at the cost of more training, right? Because if it takes longer to converge, you need more iterations. And so in this image module variable, we have hub.module, which is going to actually load a pre-trained model. And I'm going to go to this link so that we can all check it out. A comment from Ajax: recently tried Teachable Machine by Google. Hold objects in front of the webcam and it does the rest. That's really cool. Thanks for sharing. Yeah, so here's the feature vector. And so you might be wondering, what is a feature vector? Well, feature vector is a way of condensing, in other words, reducing the information content of an image. So if you give this algorithm an image, it will return a vector of several different features that it thinks are important. And those features are basically components of the image. So if it sees maybe multiple objects in the frame, that could be a feature. If it notices that one color is particularly dominant, or that could be another feature. It's actually really hard to kind of understand, um, how it might arrive at these features because it's done in somewhat of an unintuitive way. But then we can use this limited set of features to actually go ahead and train a secondary algorithm that will be able to use those features to arrive at a result, at a classification. And yeah, so this model is only 1.5 megabytes. And so it's pretty easy to learn about, hey, what are the different aspects of this model? What data did it use to train and things like that through TensorFlow Hub. Okay. So let's see. We have about 15 minutes left. So I want to see if we can get through this notebook. And then for next time, we will apply it to our plant data. Okay, so we have pre-processing images in tensors. So it's just going to take the image array and sort of give it a default size and values for each of the sort of pixels in the image, resize that, and make sure that all the images are the same size so that the features map well onto the image. And I don't know, maybe folks have seen this sort of thing before, but we're going to be training in batches. It makes it better for the model to calibrate itself when it sees the images one batch at a time. So instead of exposing the model to all the images at the same time, it will learn over a series of batches. So here's the model definition. So this is a dense layer. We will talk more about this tomorrow. I kind of just want to go through this notebook with you all on a more overview level today. But basically, we have a single linear layer, which is this dense activation layer. Oh, I'm sorry. Actually, this is, if you want to do an activation layer, you can, but we actually just have a single dense linear layer. And yeah, so that's the model for now. And for each class, the model will output some real number as a score of how much the input resembles the class. Okay, and so this is called the logits. So we have that given some features, and we apply that to the model, we will get the logits. And we can just say that whichever one has the highest probability will be our classification. Okay. And so in these next few steps, what's happening is we're training the optimizer and just sort of going through and finding the best prediction for a given feature set. And you can tell at the end of this process, we have our correct prediction variable, and we're trying to see the accuracy of those correct predictions based on our model. And so the next, I should actually be running all of these. I don't think I run this one. Okay, so now the goal is to train the network. I'm going to run this cell. You can see we have some parameters here. So the number of training steps indicates the number of batches, essentially. How many different batches will we expose the model to? The train batch size tells us how many images will exist in each batch. And the eval every parameter tells us how many times we should evaluate the model's performance. So you'll see that this happens when we get to the end of a batch. The evaluation will be calculated based on that accuracy variable. So we start off in our first batch at 27.58, and we continue increasing, but our accuracy sort of increases at incrementally smaller rates. And actually, this is kind of interesting. From step 60 to 70, our accuracy went down. Okay. So accuracy does not always go up with increased training. And in fact, in this case, we kind of reached this plateau where the accuracy wasn't really improving that much. It was going up sometimes, down other times, sometimes just a difference of 1% or so. So once we got to step 99, which means we've gone through 1,000 images, because remember there are 10 in each batch of 100 batches, that sort of indicates that we've plateaued at an accuracy of 81%. So 4 out of 5 times the model can predict the correct flower. Okay. So this is so it looks like some of these functions are going to get deprecated soon. So thank you, John Paul, for pointing that out. And these are warnings as far as I can tell. So I wouldn't worry too much about them because the code should still run. But if you want to follow the instruction to fix the deprecation, that would be pretty cool. Thanks for pointing that out, John Paul. All right, and so now we have this thing called confusion matrix. We'll talk about this more next time, but this is showing the accuracy of the model for each class. And these are just some of the incorrect predictions. So if we have a model that's making errors, which is most models, we want to make sure that the errors are not biased in any particular way, because that could actually indicate an area of improvement for us. If it's always missing a certain category, maybe we can add more training examples or account for that somehow. So, and we want to know that too, because then we don't feed it that type of image. But yeah, for example, here it was not good at predicting this. I guess this person sitting next to kind of a pink couch or something is causing the model to think that this is a rose, an image of a rose. Kind of interesting, even though it's really a daisy. That's just one example. And with the insects, it seems like insects can really mess up the algorithm. So that's good to know, because next time we have an image with an insect, we can think twice before we put it through this algorithm. Right? But you can see that we trained this model using just 2 gigabytes of RAM and a 24 gigabytes of storage space. And it just goes to show that this transfer learning thing can be really useful in these examples. Yeah, it's a pretty small disk, right? The reason why it's able to be so small is because this Google Colab is running in a containerized environment where it's only installing literally the bare bones of infrastructure for what's required to run this notebook. So it's really conservative on what it installs into the virtual machine here. Yeah, yeah, it's like an online VM. Actually, we did a workshop that I hosted on virtual machines a couple months ago, where we talked a little bit about this stuff. But yeah, so that's why it's so small. But yeah, anyway, everybody, this concludes the workshop for today because we're sort of running short on time, and I'm a little bit wary to start the next section, which is going to be applying our plant data set to this notebook. But we will save that for next time. And yeah, and the next time I'll also take any suggestions you all have from things you might like to see us cover. I don't really have it super planned out yet. Maybe we can talk about the teachable machine. I'm kind of curious about that, and I might look it up myself and see if there's any cool stuff there. But yeah, I'm glad it was informative. Yeah, I'll see you all next time for our final part of the using machine learning and data workshop. No problem. All right, everyone, signing off.